All right, this is problem 9. It's an interesting problem that can be approached in a number of ways. I'm going to kind of show you probably the simplest way to approach this problem, and that is just to count the number of dots. So I've done that here: 5 dots, 12 dots, 21 dots, 32 dots, and then to take these expressions and see if when n, the stage number, is 1, I get 5, and 2, I get 12, and 3, I get 21, and so on. And so I could do that by hand, but to save myself some time, I'm actually going to use my calculator. So I've typed each of these expressions into my calculator. Calculator wouldn't understand n, so I've put in x in its place, but it works the same way. So you can see I've listed all of these under different y equals here. And now I'm going to go to my table. And if I look across, these first two, y1 and y2, both work. And I can scroll over and see these other ones. And y3 and y4 also work. So surprisingly, each of these expressions is actually an expression that works. So that's one way to think about it, and probably the most straightforward. Another way to think about this is to look at this visually and see where these expressions are coming from. And I think that's probably, the most elegant solution to this. This one here, for instance, is coming from the fact that this square, if it was complete, if this square was complete with 4 dots in here, that's where the -4 is coming from, because it's like you're taking the 4 corners out to get this figure. And then this right here is a square. This square is 4 by 4. And so that's 2 plus 2 here. This next square is 5 by 5, but n is 3. It's this little part here, so we'd have to add those in to get 5 squared, but then again we would take away these. Okay, and each of these actually can be shown to be visually representing these. The last way that you might approach this is really just by simplifying these. So let me give you an example. I'm not going to go through all of them, but let me give you an example. This one here and this one here are pretty easy to show that they're equivalent, because if I go here and I distribute, I get n squared, and I distribute again, I get plus 4n. Okay, so that shows me that those are the same. Again, it doesn't necessarily mean that it works. They could be the same and they could both be wrong. So there has to be some way that I can know that this actually works. So for instance, plugging in 2 squared is 4, plus 4 times 2 is 8, 4 plus 8 is 12, and so that works here for this one here. So a few different ways to approach it. Yeah, hope that was helpful. Let's go on to problem number 10.